Welcome back, class. Today we're going to learn a new way to solve quadratic equations. It's called completing the square.
Error. How can a quadratic equation be a square? The graph of a quadratic equation is a parabola, not a square.
Hey, robot, why do you keep interrupting him? Why don't you look in the mirror? I think your head is a square.
Do not meddle with me, vampire. I am programmed for revenge.
V9, you've asked a good question. How can an equation be a square? We're not talking about the kind of square that's a four-sided shape. What kind of square do we mean?
I have an idea, Mr. C. When we multiply something times itself, we say we're squaring it. Is that the kind of square we're talking about?
Oh, I get it. Like 3 squared is 9, or 4 squared is 16.
That's right, Ruby and Bones. A number like 9 is called a perfect square because we get it by squaring 3. 16 is a perfect square because we get it by squaring 4. Most numbers are not perfect squares, though. For example, 5 is not a perfect square because its square root is a long, complicated number with a lot of digits after the decimal point. In this lesson, we're not focusing on numbers that are perfect squares. We're focusing on quadratic equations that are perfect squares. But it works the same way. A perfect square quadratic is what we get by squaring a single factor, like x plus 3, or x minus 5. So x plus 3 times x plus 3 is a perfect square quadratic. So is x minus 5 times x minus 5. To save ourselves time, we can write perfect square quadratics using exponents. So instead of x plus 3 times x plus 3, we can write x plus 3 squared. We just need to remember that x plus 3 squared is not the same as x squared plus 9. We cannot just square the x part and then square the 3 part. What's the right way to multiply x plus 3 times x plus 3?
We use our FOIL technique. First, outside, inside, last. When we FOIL x plus 3 times x plus 3, we get x squared plus 3x plus 3x plus 9, which is x squared plus 6x plus 9.
Well done, Ruby. Now, class, let's play a game.
Ooh, I love games.
We're going to play this game first with perfect square numbers. Once we get the hang of it, we'll play it again with perfect square quadratics. The game works like this. I'm going to name a number that isn't a perfect square, and you tell me how I could write it as a perfect square plus or minus some amount. For example, if I give you the number 10, 10 is not a perfect square, so we can't write it as some whole number squared. But it's close to 9, which is a perfect square. So in our game, I could write 10 as 3 squared plus 1, since 3 squared is 9, and 9 plus 1 is 10. If you're wondering how I thought of that answer, I just looked for a perfect square that was near 10, and then I added or subtracted the number I needed to get me the rest of the way to 10. So let's play. Who can tell me a way to write the number 17 this way?
I get how this works. 17 isn't a perfect square, but it's close to 16, which is a perfect square, like 4 squared. So 17 is 4 squared plus 1, right?
Excellent, Bones. Can anyone think of a different way we could write the number 17 using a perfect square?
3 squared plus 8, because 3 squared makes 9, and 8 more than that is 17.
Well done, Wendigo. That works too.
Ooh, I have another way. If we can use any perfect square, could we write 17 as 10 squared minus 83? 10 squared is 100, and 100 minus 83 equals 17.
Nice job, Codette. That was a good one.
Thanks, Ruby.
Good, class. You're getting the hang of this. So let's play again now, but this time let's use perfect square quadratics. I'll tell you a quadratic that isn't a perfect square, and you tell me how I could rewrite it as a perfect square quadratic plus or minus a number. For example, if we have the perfect square x plus 2 squared equals 0, then when we FOIL it, we get x squared plus 4x plus 4 equals 0. So in our game, if I give you the quadratic x squared plus 4x plus 5 equals 0, you could add 1 to the perfect square x plus 2 squared. Your answer could be x plus 2 squared plus 1 equals 0. The perfect square ended with a plus 4, so adding one more gives plus 5, which is what we're looking for. Let's play. Who can think of a way to rewrite x squared plus 4x plus 2 equals 0? Let's use the same perfect square quadratic we've already been talking about, x plus 2 squared. What number can we add or subtract to give us plus 2 instead of plus 4?
Our perfect square quadratic ends with plus 4. We want it to end with plus 2, so it is logical to subtract 2 from our perfect square. X plus 2 squared minus 2 equals 0.
That's right, V9. In this game, we can rewrite this as x plus 2 squared minus 2 equals 0. Good job.
But, Mr. Caldwell, this game is extremely impossible. When we are playing with quadratic equations instead of numbers, we have these x squareds and x's and the number at the end, and then my brain is like exploding. More numbers that we are adding after this, and then all of this equals 0. The Drac needs some help. Otherwise, I will never beat the robot at this game.
You will never defeat me. Ha ha ha.
Tom, you just brought me to the first big point of our lesson. This game is harder when we use quadratics instead of numbers. Even if we understand the idea of what we're supposed to do, that we're supposed to rewrite quadratics using perfect squares plus or minus some number, doing it still isn't easy. So in today's lesson, we're going to learn how.
Thanks for teaching us how to play this game, Mr. C. But why are we playing it? Does knowing how to play this game help us solve actual math problems?
Good question, Ruby. As a matter of fact, it does. For a second, think about something. When we play this game using quadratics, our answers always have a certain format. We always end up with a perfect square quadratic plus or minus some number, right? Do you notice that we've seen this format before? In our earlier lessons, we learned that quadratic equations can be written in 3 different forms: standard form, factored form, and vertex form. Well, one of those 3 forms has exactly the same format we see in our game. It's vertex form. We've seen how helpful vertex form can be when we're graphing. It tells us where the vertex of our parabola is located. And in today's lesson, we'll also see that it's pretty easy to solve using a method we already know, taking the square root of both sides. So this game is very useful. The only problem is that, as Tom just noticed, it's hard. We need a method to help us. And that method is what we're learning today. It's called completing the square. Completing the square means figuring out how to rewrite an equation as a perfect square quadratic plus or minus some number. Let's see how it works. Suppose that I give you the quadratic equation x squared plus 6x plus 5 equals 0. Our first step in completing the square is just to make things easier for ourselves by moving the number that's on the left side, the c value of our quadratic, to the right side of our equation. In this case, we move the 5 to the right side by subtracting 5 from both sides. That gives us x squared plus 6x equals negative 5.
But Mr. Caldwell, what are we supposed to do now? I still cannot beat the robot with this strategy.
Hold on, Tom. That's only the first step. The second step is very important. It's something we didn't even notice last time. When we were playing our game using numbers instead of quadratics, there were lots of perfect square numbers we could start with, right? When I gave you the number 17, Bones thought of the answer 4 squared plus 1. Wendigo thought of 3 squared plus 8. Codette thought of 10 squared minus 83. We could have started with any perfect square number. But it does not work that way with quadratics. We can't just start with any perfect square quadratic we want. There's one and only one perfect square quadratic that we can start with. To see what I mean, look at these examples. These are all perfect square quadratics. On the top, we have x plus 3 squared, x plus 4 squared, and x plus 5 squared. On the bottom, we have x minus 3 squared, x minus 4 squared, and x minus 5 squared. When we FOIL them, pay attention to the number of x's in each quadratic. It's always different. No 2 equations give us the same number of x's. In other words, no 2 equations have the same b value. So if we're playing our game, and I give you a quadratic that has 6 x's in it, but you try to rewrite it using a perfect square that has 4 x's or 8 x's, then it doesn't matter what number you add or subtract at the end, because the number of x's will still be wrong. That's why, when we use our completing the square technique, we have to start with the one and only perfect square that gives us the same amount of x's we see in our quadratic. If you choose the wrong one, you are guaranteed to lose the game.
Oh man, so we have to write a huge table with every perfect square quadratic ever? And then look for the only one that matches our number of x's? Oh, that's going to take forever. I'm going to be dead a second time before I can finish that.
Fortunately, Bones, we don't need to do that. We can figure this out just by looking at our equation. In fact, we have a big clue right in front of us. Look at our table again. When we FOIL x plus 3 squared, we end up with 6 x's. When we FOIL x plus 4 squared, we end up with 8 x's. X plus 5 squared gives us 10 x's. The same thing is happening on the bottom. X minus 3 squared gives us negative 6 x's, and so on. The number of x's is double the number inside the parentheses. So if we're playing our game, and I give you an equation that has 6 x's in it, then you can be sure that the perfect square quadratic you need to use will be x plus 3 squared. That's because when you double the 3 in the parentheses, you'll get the 6 x's in your equation. Or if we're playing our game, and I give you an equation with 50 x's in it, you need to start with x plus 25 squared, because when you FOIL it, you're going to end up with double that number of 25 x's. You're going to end up with the 50x you need. In other words, step 2 of completing the square is to find our b value, the number of x's we have, and divide it by 2. b divided by 2 tells us which perfect square quadratic to start with. Any other perfect square quadratic will not work. Now, I know step 2 can sound complicated, so here's a simple way to do it. Look at the equation you're starting with. It has 3 ingredients: some amount of x squareds, which we call a, then some amount of x's, which we call b, and then a number at the end, which we call c. Draw a circle around your b value, the number you see in front of the plain old x. Now divide that number by 2. Whatever answer you get, write it in your parentheses next to the x. This is going to be the perfect square quadratic you need to use. Any other perfect square quadratic won't work. So you're going to have in parentheses x plus that number squared. That's it. That's step 2. Now let's pause here and make sure we understand. In a minute, we'll return to our original problem, but let's see some examples that we can practice on. A couple of them are pretty challenging, but that's because completing the square is a powerful technique that works on any quadratic equation. So sometimes we end up using it on hard equations with big numbers or tiny fractions. Don't be intimidated. Completing the square still works the same way. So let's do our first 2 steps of completing the square with these 4 quadratics. In our first step, we move the number at the end, our c value, to the other side of the equation. In other words, we move the number on the left side over to the right side. Our second step is to look for the amount of x's we have, our b value. If it helps, you can circle it. This is the number we divide by 2. That answer tells us which perfect square quadratic we need to use. So we put that answer, b divided by 2, right into the parentheses of our perfect square quadratic, because we know that no other perfect square quadratic will work. Does everyone understand?
I think we get it, Mr. C.
Good. Now let's continue solving our original problem. In our original problem, I gave you the quadratic x squared plus 6x plus 5 equals 0. We did step 1, where we moved the 5 to the other side and got x squared plus 6x equals negative 5. Then we did step 2, where we looked at our b value, positive 6, and divided it by 2. That answer, 3, told us which perfect square quadratic we needed to use, x plus 3 squared. Now we're ready for step 3. Before we jump into it, let's just remember what we're trying to do here. The whole point of our game is to rewrite an equation so that we have a perfect square quadratic plus some number, right? Well, so far we figured out which perfect square quadratic to use. That's what we're trying to get to. But that's not quite what we have. When we FOIL x plus 3 squared, we get x squared plus 6x plus 9. On the left side of our equation, we have x squared plus 6x, but we don't have the third part yet. We don't have the plus 9 at the end. So our third step is to fix that. We're just going to add the amount we need. In this case, we're missing the plus 9, so in step 3 we're going to add 9. That's going to turn the left side of our equation into exactly the same as x plus 3 squared, since that's what we've been trying to do this whole time. Of course, if we're going to add 9 to the left side of our equation, we know that we also have to add it to the right side of our equation. Right now, the two sides of our equation are equal, so if we add 9 to just the left side, then our equation won't be equal anymore. That would be like if we had a seesaw where Tom and B9 were perfectly balanced on opposite sides, and then I asked Wendigo to sit on one side of it. Not so equal anymore.
I would not do this to my friends, the robot and the vampire.
When we add 9 to both sides, we get x squared plus 6x plus 9 equals negative 5 plus 9. Now we just simplify what we have. On the left side, we have the perfect square we've been wanting all along. We can finally rewrite our left side as x plus 3 squared. On the right side, negative 5 plus 9 simplifies to positive 4. So our whole equation is now x plus 3 squared equals 4. We're done with our third step. To make sure we understand this step, let's pause and practice it on those other examples we saw earlier. In our third step of completing the square, we add something to both sides. Who remembers how we figure out how much to add?
We are trying to make the left side of our equation into a perfect square quadratic. We figured out which perfect square we wanted, so now we FOIL that perfect square. This shows us what number we are missing. We need to add this number, the c value, to both sides of our equation.
Excellent, Wendigo. Let's do it. When we FOIL our perfect squares, the c values we see at the end are plus 1, plus 4, plus 9/4, and plus 100. And we can see that the left sides of our equations don't have those amounts yet. Since we're trying to turn the left sides of our equations into those perfect squares, we need to add the c value to them. That means we also have to add the same amount to the right sides of our equations, so that we're keeping the equations balanced. Now we simplify our equations. On the left side, we can finally write our perfect square quadratics. On the right side, we add our numbers together. Now all we have to do in step 4 is whatever our math problem is asking for. A math problem could ask us to convert this into vertex form, or it could ask us to solve for x. Either way is pretty straightforward from here. So let's see how to do both of those things in our original problem. In our original problem, we had x plus 3 squared equals 4. If a math problem asks us to rewrite this in vertex form, we are very close to vertex form already. Who remembers what vertex form looks like?
In the vertex form, we have a parenthesis squared plus or minus a number equals 0.
That's right, Tom. So all we need to do here is move the number on the right side of our equation back to the left side. We subtract 4 from both sides and get x plus 3 squared minus 4 equals 0. That's it. That's vertex form. We're done.
Wow, that was fast.
Now, what if our math problem asks us to solve our equation for x rather than to write it in vertex form? If we go back to our equation x plus 3 squared equals 4, how do we solve that?
Mr. C, you said earlier that we could use our technique of taking the square root. I think I know how we can do that. When we take the square root of both sides, we put a square root sign on both sides of our equation. On the left side, we have the square root of our perfect square, and those two cancel each other out, since squares and square roots are opposites. That leaves just x plus 3. On the right side, we have the square root of 4. That has two different answers, positive 2 and negative 2.
Excellent, Ruby. That is how we take the square root of both sides. And you remembered something important. When we take the square root of a positive number like 4, we get two answers, not just one. There's a positive square root, like positive 2, and there's also a negative square root, like negative 2. Since we have two answers, we have to solve both of them. So we split this into two separate equations and solve them separately. Our equations are x plus 3 equals 2 and x plus 3 equals negative 2. Who can solve these?
In both equations, we subtract 3 from both sides. In the first equation, our answer is x equals negative 1. In the second equation, our answer is x equals negative 5. Both are correct solutions. Our answer is x equals negative 1 and x equals negative 5.
Nice job, V9. So let's make sure we understand this step by returning to our example problems. At the end of step 3, our equations look like this. Now, in step 4, we just do whatever our problem is asking for. So if our math teacher asks us to rewrite these in vertex form, what do we do?
Mr. Caldwell, I am becoming the world expert of the vertex form. Rewriting these equations in vertex form is very easy for a math genius like me. All that I need to do is move the number on the right side to the left side. Then all of these equations have a parentheses squared minus this number equals 0. Beepity-poppity-boo, I am finished.
You're right, Tom. If you move the number from the right side back to the left side, these equations are now in vertex form. That's it. Okay then, let's say that our math problems ask us to do something different instead. What if they ask us to solve these equations for x?
We can use the technique that Ruby recommended, taking the square root of both sides. We write a radical sign on both sides of each equation. On the left side, we now have the square root of a quantity squared. Square roots and squares are opposites, so they cancel out. We are left with whatever is inside the parentheses. On the right side, we take the square root of our number. And if this means taking the square root of a positive number, we must remember that there will be two square roots, a positive square root and also a negative square root.
Excellent, Wendigo. Now let's notice one small thing. In one of our equations, we don't have a positive number on the right side. We have the square root of a negative number. Look at our equation x minus 2 squared equals negative 9. When we take the square root of both sides, it becomes the square root of x minus 2 squared equals the square root of negative 9, which means that x minus 2 equals the square root of negative 9. Does negative 9 have any real square root? Is there any number, anywhere on the number line, that we can square to give us a negative number?
No, negative numbers don't have real square roots. You taught us that some parabolas never touch the x-axis. They turn around and head in the other direction before they ever reach the x-axis, so they have no solutions for y equals 0. I think this must be a quadratic equation like that. It has no solution, because a negative number has no real square root.
Wow, Codette, that's phenomenal. You're right. Our answer for that equation is that it has no solutions. So what about these other three equations? They all have two square roots. How do we finish solving equations like those?
I can answer this one too, Mr. Caldwell. When there are two square roots, the DRAC solves each square root separately. The positive square root makes one equation. The negative square root makes a different equation. The DRAC solves them both. And this gives us two different answers.
Well done, Tom. We just solved for x. You really hit the nail on the head.
Teacher, can I hit a nail on the vampire's head?
You ignoramusaurus! It's a figure of speech! He is saying that I am a math genius!
If you are a math genius, then I am Frankenstein.
You oversized trash compactor! Who ever heard of a monster called Frankenstein? He's called Frankenstein! Why can't you be quiet and stop interrupting Mr. Caldwell when he is complimenting me?
Vampire, I have had enough of you. Prepare to suffer my revenge.
Boys, that's enough. If you can't leave each other alone, I'll have to send you to the principal. Now, what do you want to say to each other?
That is a pretty good trick, robot. Shooting electricity out of your hand. I wish I could do that.
Thank you. It is a new upgrade on my model version. I am also equipped with a flamethrower. Would you like to see it?
Absolutely. Please not aimed at me.
V9, no more weapons in class. And if you boys really have worked this out between you, then let's get back to math.
I apologize for the disruption, Mr. Caldwell.
Affirmative. Please continue.
Alright, let's quickly review completing the square by practicing on 3 problems that look hard but aren't as bad as they appear. The first quadratic looks hard because it begins with 3x squared instead of x squared. The second one looks hard because it begins with negative x squared instead of positive x squared. And the third one looks hard because there are no x's in the middle. There appears to be no b value. But in all 3 cases, we're going to be able to complete the square. We're just going to add one small step at the beginning, a common sense step that turns the equation into what we want. The rest of the process is the same. Here goes. With our first equation, common sense tells us that we have 3x squared, but we would rather work with plain old x squared. How can we do that?
I have an idea.
I bet it is a very good idea, my friend.
Thank you, my friend.
What's your idea, V9?
We can divide both sides of our equation by 3. When we divide 3x squared by 3, it will give us simply x squared.
You're right, V9. That is what we want to do. Dividing both sides by 3 will give us x squared minus 2x minus 15 equals 0. Remember, we have to divide every part by 3, not just the 3x squared at the beginning, and not just the 0 on the other side. Our b value and our c value also have to be divided by 3. But once we do that, we have a quadratic that doesn't look so hard anymore. It will definitely work with our technique of completing the square. With our second equation, common sense tells us that we don't want to work with a negative x squared. We would rather work with a positive x squared. Who can think of a way to turn our negative x squared into a positive x squared?
Mr. Caldwell, this time I have an idea.
Silence, everyone. A math genius is about to speak.
I'm flattered, old friend.
My pleasure, old friend.
Go ahead, Tom.
I will multiply both sides of this equation by -1. When I do this, the negative x squared at the beginning of our equation, which is really -1x squared, will change into a positive 1x squared, because I have learned in this class that a negative times a negative equals a positive. We must do the same negatifying with the other parts of this equation too, so we will have positive x squared plus 10x minus 11. On the other side of the equation, we will have only -1 times 0, which is still 0.
That's right, Tom. We can turn our negative x squared into positive x squared by multiplying both sides of our equation by -1. We just need to remember what you said. We have to distribute that negative to each part of our equation. So we do get x squared plus 10x minus 11 equals 0. Lastly, with our third equation, common sense tells us, well, actually, common sense tells us to solve this using a different method. Completing the square is a slow and awkward way to solve this one, but I want to show you that we can still do it. The key is to remember that when we have no x's, like in this problem, we still do have a b value. That b value is 0. We have 0 x's. So we can rewrite our equation as x squared plus 0x minus 49 equals 0. Now that we've made these small changes, these equations look a lot more manageable. We can use our completing the square technique exactly the way we normally would. First, we move the number from the left side of our equation to the right side. Then, we find our b value, meaning the amount of x's we have. We divide this by 2, which tells us the perfect square quadratic we need to use. Because, remember, if we tried to use any other perfect square, it won't work. The perfect square quadratics we need to use are, in our first quadratic, x minus 1 squared. In our second quadratic, x plus 5 squared. In our third quadratic, as weird as this sounds, it's x plus 0 squared. Again, this is not the fastest or smoothest way to solve our third quadratic, but it does work. In our third step, we complete the square by adding whatever number we need. To find out what that number is, we FOIL our perfect square quadratic to find out what its c value is. That c value is how much we need to add. And we add that same amount to both sides of our equation. Great! The left side of our equation is now the perfect square we wanted, so we can write it as that quantity squared. On the right side of the equation, we just add together the numbers we see. We're almost done. Our final step is to solve this in whichever way our math problem is asking us to. Usually, our math problem will either ask us to write the equation in vertex form, or, more often, to solve it for x. That's it. To get our vertex form, we move the number from the right side of our equation back to the left side. Or, to solve our equation, we take the square root of both sides. If we end up taking the square root of a positive number, we need to remember that it has two square roots, a positive and a negative number, and we have to solve for both of them. On the other hand, if we end up taking the square root of a negative number, we have no real square roots, because this is a parabola that has no x-intercepts, no zeros at all, so that's what we write as our answer. No solutions. Good work today, class! You've just learned one of the most challenging topics in quadratic equations. I'm very proud of you. Keep up the hard work, and I'll see you next time.